Looking at this visualization of data nodes rapidly connecting across a geographic void, you see the primary directive of the early internet: aggressive expansion. In 1969, a government organization called ARPA wanted a network resilient to military attacks. Security against local deception was not the goal; survival was. To build this, ARPA sent a request for proposal to Bolt, Beranek and Newman, an acoustics company. Their task was to design the very first hardware capable of reliably transmitting messages between massive mainframe computers. Look closely at this original steel interface plate. This is the Interface Message Processor, or IMP, developed by BBN. It was the first dedicated hardware router on the ARPANET, translating the theoretical concept of data routing into physical machinery. This wide shot of a UNIVAC installation shows the reality of computing at the time. These machines took up entire rooms. They were highly isolated. The sheer logistical difficulty of getting two mainframes to exchange data meant that simply establishing a successful connection was an engineering triumph. Because these were closed systems requiring strict physical access to even approach a terminal, the protocols were designed to implicitly trust any connected hardware. If a device was on the network, it was assumed to be authorized. We still inherit that exact legacy assumption of absolute trust today. Every time you connect to a local area network, or LAN, you interact with protocols built for the enclosed, trusting environments of the 1970s. This blueprint illustrates a modern LAN, a dense web of endpoints, physical tables, and central switches routing packets between workstations. But freezing the traffic to look strictly at the hardware layer reveals a critical vulnerability. These base routing protocols possess zero built-in cryptographic authentication. This means ethical hackers do not necessarily need to crack complex encryption algorithms to compromise a local network. They just have to lie to the foundational protocols that manage the traffic. The entire discipline of network penetration testing relies heavily on weaponizing this structural trust deficit. The lowest layers of the network architecture are engineered to believe whatever they are told. To see exactly where this exploitation happens, we use the OSI model. This side-by-side comparison shows the 7-layer OSI framework next to the 4-layer TCP/IP model. Both dictate how data is encapsulated and formatted before transmission. When a packet is transmitted, it travels down the stack. Starting at the application layer, it gathers new formatting instructions at each tier, building up a larger set of headers until it reaches the physical layer to be pushed out over a wire. The vulnerability begins here at layer 3, the network layer. This is where logical IP addresses are attached to the packet, allowing it to be routed broadly across the internet. As the packet drops to layer 2, the data link layer, those logical IP addresses must be translated into physical, hard-coded MAC addresses. This wraps the IP packet in a format that local switches can actually process. Hardware devices cannot physically route traffic using logical IP addresses alone. They require physical MAC addresses. The seam where these two layers interact, where an IP address is mapped to a physical device, is the most vulnerable attack surface on a local network. We see this vulnerability clearly when a device first joins the network. This diagram shows a new computer connecting and broadcasting a request for a working IP address using the Dynamic Host Configuration Protocol, or DHCP. The central DHCP server receives the request, selects an IP address from a limited pool, and assigns it to the new computer for a set lease period. The critical flaw in this exchange is that the DHCP server performs zero identity verification. It does not ask for credentials, passwords, or proof of authorization from the requesting hardware. This automated convenience creates an exploitable pool of trust. A rogue client can continually spoof MAC addresses to request new IPs, exhausting the server's pool entirely, or impersonate legitimate hardware to intercept data. Once devices have IP addresses, they still need to talk to each other physically. To cross that gap between Layer 3 IPs and Layer 2 MAC addresses, the network relies on the Address Resolution Protocol, or ARP.
Let's look at a normal ARP operation. Here, the red computer wants to send data to an IP address ending in .33. Because it doesn't know the physical location of that address, it sends a wide broadcast across the entire network asking, "Who has 192.168.1.33? The yellow computer receives the pulse, recognizes its own IP address, and replies directly to the red computer, handing over its physical MAC address so the data transfer can begin. To save time, the red computer caches this mapping in a local directory called an ARP table. Now, any future traffic destined for .33 will automatically go to that MAC address. But ARP operates entirely on an honor system. Any device that asks for a MAC address will unconditionally trust the first response it receives. There is no mechanism to verify the responding computer is telling the truth. This blind trust is exactly what allows an unauthorized actor to intercept live network traffic. Returning to our LAN diagram, a malicious blue computer has connected to the network. It sits quietly and monitors the traffic until it sees the red computer broadcast an ARP request for the yellow computer. Before the legitimate yellow computer can reply, the attacker fires a forged response back to the red machine. The blue computer lies, claiming that it holds the requested IP address and provides its own MAC address instead. The red computer receives this forgery and updates its ARP table immediately. The legitimate entry for the yellow machine is completely overwritten by the attacker's MAC address. As a result, every packet the red machine attempts to send to the yellow machine is now physically routed directly to the attacker. The attacker now controls the flow of reality for the target. By silently forwarding the traffic along after reading it, the attacker captures all unencrypted data passing between the two machines without triggering a single system alarm.
Network administrators can observe this raw data on the wire using packet-sniffing utilities like Wireshark, but spotting the attack requires knowing exactly what to look for. Look closely at this mock-up of Wireshark displaying a forged ARP packet. Down below, we can see the exact hexadecimal and ASCII breakdown of the traffic. If you examine the packet headers, you will find a source port, a destination port, and a length. What you will not find is a cryptographic signature or any form of identity validation. Because the forged packets are structurally perfect, the network hardware itself cannot mathematically distinguish a legitimate routing response from a malicious forgery. The data link layer simply executes what the packet instructs. If the lack of authentication is the problem, it seems obvious that engineers should simply release a secure version of ARP or UDP that mandates identity verification. But verifying identity requires cryptographic handshakes, similar to how TCP negotiates connections. Introducing that level of latency and computational overhead to every single physical connection on a local network would severely degrade its speed. Furthermore, redesigning Layer 2 protocols would require replacing the physical hardware and firmware of nearly every router and switch currently operating on Earth, just to maintain backward compatibility. The technical reality is unavoidable. The foundational routing layers of the Internet are permanently and inherently insecure by design. The speed that makes the network functional also makes it vulnerable. Since the physical network itself cannot be trusted to verify identity, security must be decoupled from the routing infrastructure. As shown in this updated topology, the modern solution relies on high-layer cryptography, like SSL, TLS, and VPNs. These protocols operate high up in the application and presentation layers, creating a mathematical tunnel independent of the physical cables. By encrypting the payload before transmission, we ensure that even if traffic is physically intercepted by a man-in-the-middle through an ARP spoofing attack, the data remains mathematically unreadable. Ethical hacking exposes a definitive rule of modern computing: never trust the network beneath you. You cannot secure the wire, so you must mathematically protect the data itself before it ever leaves the machine.